Hi. Section 7.4, Zill and Wright present us with more properties of Laplace transforms, and I'd like to talk about some of those right now. So for starters, just to remind you what we're doing, we are thinking about shortcuts or other results that we might find useful in our work with ODEs and with taking Laplace transforms and their inverses. So why don't we try something in transform space? Okay, so I've talked before about Laplace transform space, or I might even think of calling it S space. It's the, instead of time, we've replaced time with this other variable. So remember that we're given some new function, capital F of S, which is the Laplace transform of f of t. So when I talk about Laplace transform space or S space, all I'm really talking about is we used to have a function defined from 0 to infinity on time, and now we've changed it in a way by transforming it. We've changed it into a function in S space. So let's try taking the derivative in S space. We have a function of S, so what happens if we take f prime, capital F prime? Let's just do that. F prime of S. In other words, dds of f of S. Well, we know what that is. That's pretty straightforward. Just go back to its definition. Integral from 0 to infinity of the Laplace transform kernel e to the minus st times our original function f of t dt. Right? That's just what it is. So we're just saying what new results might we get if we took this derivative? Well, notice that this derivative is the Laplace transform space variable S. Doesn't care about t, doesn't care about the limits of the integration. That's all a time thing. This is 0 to infinity in t. So it really only sees one thing. This dds only really sees that s right there. So we can easily take that derivative. It just brings down a negative t. So this is just the integral from 0 to infinity. So I'm just bringing this in here. It's only operating on this. So it just brings down a negative t e to the minus st. So that's the s derivative of that. Nothing else gets its derivative taken, so it just remains f of t dt. And so notice I can pull the negative out, and I can take the t over near the f of t. So then it becomes e to the minus st times t, well, times f of t times t dt. Okay? Let's check that out. In other words, I just showed that now it's, well, I can just interpret this. This is the Laplace transform of this thing. Right? So it turns into the Laplace transform of t times f of t. Now, so let me just summarize that by saying sort of the result from here is, I'm just picking up here, if you take the Laplace transform of t times some function of t, it's just equal to minus dds, right? That's what we started by doing. I'm flipping the negative sign over here, of the Laplace transform of f. So whether I write it this way or whether we look at f prime and we find that it's this, either way I'm just saying, it's a result. I mean, I'm trying to be honest in my reaction to this. I don't know what to say about this. It's weird. It could be deep, but the bottom line is that this is true. So it provides. It's a result. It's like, you know, if you turn on this highway and drive 100 miles, you get to this destination. Similarly, this is just something that turns out to be true. What's useful for us in our work is that we might use it as a shortcut or as a way of calculating something more efficiently. Okay? So absorb, mull this over, but you know, the main thing is to know it. I don't know how deep it is, but I do think that it's useful. Okay? As a matter of fact, there's more than just this. We could take two derivatives of the transform, and all of this is part of a larger theorem. I'm not going to keep going. I'm just going to quote the theorem to you. I'm later going to refer to this as the T-power theorem, but for now let's just call it 7.4.1. So that is just that if you're given a Fourier transform, which is capital F of S, it's the Fourier transform of some function, then the Fourier transform of any power of time, T power, times f of t, is minus 1 to the n times the nth derivative, dsn here, of the Fourier transform. Okay? I like to call that the T-power theorem. That is not the official name of the theorem. That's my name. But this is this result. So once again, I don't know what to say about this as far as depth goes or anything like that, but this is true and useful. Okay, so let me give you an example of how it might be useful. So first let me step back, take a picture of that. All right. How is this useful? Well, once again, we are using, the way we take Laplace transforms, or even their inverses, is using these tables. So let's say we had as an example, we wanted to take the Laplace transform of t squared times cosine of 3t. Right? Okay, well, so for starters, you look in the table, it's not in the tables. It's a combination of two functions that are in the tables, but it's not in the tables. So we have our choice. We can use some result that we have sitting around, or in this case for the Laplace transform, we could actually calculate it explicitly. Because of the t squared, I can tell you integrate by parts twice. But yeah, I think both of these are of exponential order, so I think that should be fine, right? So, but it's going to be some work. So let's use this theorem instead. Okay. In particular, it's useful to use the theorem because we do know that the Laplace transform of cosine 3t is pretty straightforward. That's just s over s squared plus 9. Okay, so we can use the t-power theorem with n equals 2. You see t squared. Use the theorem with n equals 2. So that means I just have to take minus 1 squared, so there's not going to be any negative sign in front, and then I have to take two derivatives of this. So let's do that. DDS of the Laplace transform, so this is sort of my capital F of S, and this is t squared, so we're going to take two derivatives of that. So two derivatives, let's do the first one. S over s squared plus 9, so that's 1 over s squared plus 9 minus s over s squared plus 9 squared times the derivative of what's inside, which would be 2s. So I apologize, I don't like or use the ratio quotient theorem, I guess it's called, the quotient rule. You should do this derivative, you should do this entire example using the quotient rule. I will not be doing that. I'm just going to keep them as, just treat this as a separate polynomial. So this is 1 over s squared plus 9 minus 2s squared over s squared plus 9 squared. Okay, so that's one derivative. Now I need to take the second derivative. Right? We want the second derivative of this function f. So that means first derivative, another derivative of this. Okay, I'm not going to recopy it, I'm just going to do it. So this is now, so I need to take a derivative of this and a derivative of this. So this one's going to be straightforward because there's an s in only one place, so it's going to be minus 1 over s squared plus 9 squared times 2s, derivative of what's inside. And then here I've got to do the numerator and the denominator, so this just gives me minus 4s. Yeah, that's correct, 2 times 2, and then the denominator stays the same, s squared plus 9 squared. And now I've got to do the denominator. So this is going to bring up a minus 2, so it's going to be plus 2 times 2 is 4. The s squared stays the same. taking the derivative of the denominator, so, oops, don't let these get too close. Derivative of the denominator is going to be s squared plus 9 cubed. The negative 2 already came up. Derivative of what's inside is times 2s. Okay? Hope that wasn't too fast. So I can see that these two are going to combine. This is going to be minus 6s. This is going to be 8s cubed. This is going to be minus 6s. And then now I will connect with your method of doing this with the quotient rule. I'm going to multiply, I need to get common denominator, so I'm going to multiply minus 6s by s squared plus 9. So this is going to be 8s cubed minus 6s times s squared plus 9 divided by s squared plus 9 cubed. That's the answer. Okay, that's the answer to the Laplace transform of that. Okay, and we took care of the negative 1 squared by not doing it because it's n equals 2 in the theorem. Okay, so you pause it here, see if that's what you get. Okay, hopefully I didn't make any mistakes. So I know that seems a little bit involved and cumbersome to go through that calculation, but believe me, it's much easier than doing the integration by parts twice. And you know, I don't really need to insist on that. It's easier, okay. I don't know if it's easier, it's just another way of doing it. So it's good to have options. Cheers. Drink your coffee or your water. So let me just make a quick word. There's this nice little note in Zill and Wright. Okay, so we have this example. There's this nice little note in Zill and Wright about using these theorems, and I don't want you to miss it. It's a small comment. I think it's sort of 2/3 of the way down, page 302. They say, well, I don't remember exactly what they say, but they're talking about taking the Laplace transform of t times e to the 3t. Okay? How would you do that? It's not in the tables. So we want to use one of our results, right? But what's interesting is, in fact, this is the example they gave, but if it was t squared, it would be true as well. There are two different theorems we have to deal with this. And I'm going to put them in, let me make sure I have blue here. I'm going to grab my blue chalk, excuse me. So, the t power theorem, I'm going to do that one in blue. In this case, this would be n equals 1, and then this would be f of t. Right? So we'd be taking we'd be taking one derivative times negative 1 of the derivative with respect to s of whatever the Laplace transform of this is. Right? But there's another theorem, which is the translation theorem, or what I like to call the shifting theorem. I'm going to note in red, and in this case, this would be your function f of t, the linear one would be f of t, and then this would be the shift with a equals 3. Right, so we take the Laplace transform of t, and then we would shift it by some amount according to that theorem with a equals 3. Okay, so notice that there are two different ways. So I'm just going to say two different ways to get the Laplace transform of this function. Okay, and they discuss it in the text, but it's not unusual. So we should start to expect this now. It's sort of, you know, like a suitcase with two handles. You can grab it on the top, you can grab it on the side. You can pull it by the wheels, or you can just carry it along and it's not touching the floor. It's two different ways of approaching this function based on these two different theorems. Okay, that's sort of a nice point. All right. So this leads into the next question. It's one function times another function. We're interpreting them in two different ways. Is there anything more general? Are there any results that are more general? So I'm drawing a line. This is a new topic. Any more general results. This is for t. This is a t-power theorem. That's with t to the n. The shifting theorem, or the translation theorem, is with the exponential of at. Is there anything more general? Any more general theorem for the product of two functions? So I left the L out. General. Given some function f of t and some other function g of t, now more general, not exponential, not linear, but just let's speak more generally. Is there any way to get the Laplace transform of the product of those two to be anything interesting? We're just asking, right? I think that's a very natural thing to ask at this point, as we start to see that a lot of these theorems involve some function times something special. Let's just go all the way, right? What's coming next? So not just g being linear or not just g being exponential, you might think, well, maybe this is just the product of the two Laplace transforms. But I'm going to not confuse you, and I'm immediately going to tell you that this is not true. The Laplace transform of f times the Laplace transform of g, it doesn't work that way. Okay, this is one of those things that you probably wish was true, and I might wish it's true, but it's not. Okay, this does not work. We might hope that it would work. I guess it didn't really work for this, right? It was something more complicated. It didn't just come out that this was, we would have noticed, I think, if that was the case. It didn't come out, so I guess we could have guessed this, right? It's not going to work. However, there's something really close to this that does work. And that brings us to the next topic in 7.4, which involves convolution. Okay? So you might want to pause and run around the block or something like that. This is a little more involved. In fact, I don't know if you've seen this before. I sort of feel that you have, but I'm not 100% sure. Convolution, it may seem a little odd if you've never seen it before. You give me two functions, f and g. Let's speak from 0 to infinity, f of t and g of t. And this is called the convolution of one with the other. So this is something new and a little weird. It's like multiplying the two functions, but you're multiplying and integrating them together. You're convolving them is what it's called. We write it as f star g. F is convolved with g. The convolution of f and g, it's going to be a function of time. In fact, it's the integral from 0 to t of, let me get it right, f of the dummy variable tau times g of the of the function t minus tau. It's the argument g of t minus tau d tau. Okay? This is the definition. That's 0 to t. This is the definition. It's we don't really have time to discuss it. Where it comes from a lot of different applications. I think it first came up in signal processing. Not 100% sure of that, about the history, but it is often used to take two different functions and say, well, what if I multiply them in this sort of off way? One of them is functioning as the kernel in a way, but we're just taking these two functions and multiplying them by each other in this way of integrating from 0 to t. Okay? I'm not going to say much more about that. This is just sort of a definition. We're just going to have to take it, other than taking it as a special way to combine f and g, we're just going to take it for what it is, the definition. Okay? All right? To some extent, for the purposes of Math 250, I'm going to motivate this definition by this beautiful, beautiful theorem that's next, okay, which is called the convolution theorem, which I think you're going to like. It's also 7.4.2 in the text. And it goes like this. Given f and g, so let me rewrite that. Given f of t and g of t, two functions, we're going to require that they're at most piecewise continuous. Really, they just need to be integrable in the sense that we've been talking about up until now. Continuous on the domain 0 to infinity, and exponential order, that just means that their Laplace transforms exist. Right? We talked about that before. They don't grow faster than exponential. Then the Laplace transform of the convolution of f and g is the Laplace transform of f times the Laplace transform of g. Isn't that great? Okay? This is the convolution theorem. I could have motivated this by saying, wow, what we were just talking about, wouldn't it be great if you could somehow take the Laplace transform of the product and get the product of the individual Laplace transforms? What could I do to these that would make this be true? That would be one way to motivate the definition of the convolution. It would be a little backwards, but I mean, you could have said, I want this so much, right? I really want to have this bottom line, which is that I want to know what happens if I multiply capital F. Let me write it a different way. Given that the Laplace transform of F is capital F of S, and the Laplace transform of G is capital G of S, then what is capital F of, what happens when I multiply these? What's that equal to? All right, well, the answer is, it's the Laplace transform of the convolution of F with G. All right? So, in other words, convolution in time is the same as multiplication in Laplace transform space. If you're following along in the world of Laplace transform space, or what we might call S space, just purely multiplying two functions in S space is convoluting them in regular space. Okay? That might be a little deep. Okay, so you might want to meditate on that. This is just a different statement of the theorem. Okay? However you want to remember it, I strongly suggest you remember it. Okay? So what's next? Examples, uses, and other things. That's all for now. Thanks.